All right, let's go ahead and do this homework. Explain how bouncing a cold basketball causes it to bounce better. So what is it about bouncing the ball makes it bounce better? What? It's not, it's less dense. What makes a basketball bounce? How about this? When does a basketball not bounce? When it's deflated, right? So what you need to have is it to be as inflated as possible. I'm sure you've bounced a basketball or some other ball that's overinflated, right? It doesn't feel right, it bounces up too high. So what you need is the pressure inside of the ball to be just right. Too little, doesn't bounce high enough. Too much, bounces too high. So how can bouncing the ball, so if it's cold, and is the pressure too low or too high inside of it? It's too low. So how does bouncing it increase the pressure? Warms it up. So what does that mean? Gets the gas particles moving faster, right? So the fact that you're throwing the ball to the ground and the ball and the gas particles in the inside are getting slammed against the inside of the ball, that makes them move faster. Just like if you were inside of a van and you had to stand up and then somebody slammed on the gas, you'd probably slide against the back. And then if they slammed on the brakes, you'd slide against the front. And if they turn hard left or hard right, you'd slam against the walls. So that's what you're doing to the gas particles inside of the basketball. So in essence, you're making them move faster. So all right, so how many moles of gas would be present? So we've got an ideal gas law problem here. How do you know this is ideal gas law and not Charles law or one of the other ones? Nope, because there's Avogadro's that's got moles in it, Avogadro's law. There's only one of anything, right? There aren't two pressures or two volumes or two temperatures. There's only one of each thing. So I need moles. There doesn't seem to be any moles present in this problem, but this is an ideal gas law problem, so what I can use is the ideal gas law constant. So I'm going to write so that's the unit, right? I've written it upside down. Is that okay? Right? I mean, it doesn't matter. These things are equal to each other. 1 mole times 1 liter divided by 0.08206 liters times atmospheres. The numerator and the denominator are equal to each other. So you can flip it around however you like. And in this case, we're looking for moles, so I want to flip it around so I can get moles in the numerator. So now to do this problem, I just need to get rid of the liters. I need to get rid of the atmospheres, and I need to get rid of the Kelvin. So let's do the Kelvin part. 273 over here, and I get 298 K. So if I put 298 K down here, 8K, I can cancel out the Kelvin unit. And then the atmospheres is easy. It's 2.5 ATM. And I can cancel out the atmospheres. And then, so I've got 100 milliliters, and it's 1,000 milliliters is 1 liter. So the milliliters cancel, and then the liters cancel. And I got 0.01 mole. So, looks like I should have 3 sig figs. I didn't take it out that far. That's still only 2 sig figs. Does anybody have that to the 3rd sig fig? No? It's all right. Okay, so in this particular problem, we're looking for molar mass. I want to calculate the molar mass of this gas. So what are the units for molar mass? which is the number off the periodic table. So what are those units? Grams per mole. So in this, I need to have grams over moles for my answer. So I was given grams, so I'm going to go ahead and write 9.5 grams right there. And now I need moles. So I'm going to write 0.08206 liters, atmospheres, mole, Kelvin. So now I've got my two units and I've got them in the correct spots, the grams up top and the moles in the bottom. So I need to get rid of Kelvin, liters, and atmospheres. So the liters, I'll throw a 3 liters down here and cancel the liters out. This says that standard temperature and standard pressure is 1 atm. So the atms cancel. And then standard temperature is 0 Celsius. So that's 273 Kelvin. And so that cancels out. And the only thing I've got left are my grams divided by my moles. And it works out to be 70.9 grams per mole. If I told you that this was an element, this gas was an element, could you tell me which element I'm talking about? Chlorine. Why is it chlorine? He's right. Cl2, right? One chlorine is 35.453, but two of them is about 70.9. So if this was an element, the only element that it would match up with is chlorine. Most of the time when I ask that question, what people will do is they'll run and they'll find whatever the molar mass is closest to 70. So what is closest to 70? Which one of those? It's a metal, isn't it? Say again? Gallium. Yeah, okay. So it's not right on 70.9, and it's also probably not a gas since it's metal. All right, so I've got xenon, and it's traveling 150 miles an hour in a container, and also in that container I've got some helium. So what I want to know is how fast the helium is moving. So this is, if I'm talking about speed, this is a Graham's law problem. So I'm going to do the rate of my helium divided by the rate of my xenon. I always do the slower gas in the denominator and the faster gas in the numerator. That way I get a number greater than 1. And so then this is going to be the molar mass of xenon, which is 131.29, divided by the molar mass of helium, which is 4.0026. And if you do that, you end up with 5.7. So that's 5.7 over 1. So what the 1 means is this is the speed, the rate of the xenon, and then the 5.7 would be the rate comparable to the helium. So if your xenon's moving 1 mile per hour, your helium is moving 5.7 miles per hour. So if we know in this problem that the xenon is moving at 150 miles per hour, how fast is the helium moving? And I got 855, so 860 miles per hour. Okay, that seems good. All right, so this next problem is kind of jerkish, but whatever. All right, we've got pounds, and we've got feet and feet and feet, and we've got Fahrenheit, and we want a pressure. This is a ideal gas law problem, so what we're looking for are liters, atmospheres, moles, and Kelvin. So none of those units work out for us, so that we're going to have to do a whole bunch of unit conversion stuff. I think the first thing that I'll do is this 70, and then I'll subtract off 32 and multiply it by 5/9. And I'll get this to be 21 degrees Celsius, and I'll add 273 to that, and we'll get 294 K. All right, so I got the temp part taken care of. There's a volume issue and there's a pounds issue. I'm gonna do the volume issue. So this is 3 feet times 2 feet times 4 feet. So that's feet cubed. And I need to get to volume. So feet times feet times feet is a volume unit, but I need to get to the metric volume unit, which is liters. So I can go from cubic feet and get to liters. So what I'm going to start off with is 1 foot is 12 inches. The problem with this is there's 1 foot in the denominator. There's still 3 feet in the numerator. So what I can do is either write that same thing 2 more times, or I can write cubed feet, cubed inches, cubed, and cubed 12. I just cube everything. And that's okay. It's the same thing as multiplying 12 inches by 12 inches by 12 inches. So I cancel that out. My feet cubed cancel. And then I need to get rid of these inches cubed. So inches cubed is going to have to go down here. And then I can go from inches to centimeters. So that was 2.54. And we still need to have that thing cubed. Since I have the inches cubed, all the numbers have to get cubed. And so then my inches disappear. And then the whole reason we were doing this is because of this unit conversion. Milliliters and centimeters cubed are equal to each other. So just throw a 1 up there. And now I can easily go from milliliters, 1,000 milliliters, to 1 liter. And when I do 1,000, and so then I get 600, liters. So I got liters here. So now I've got liters and I've got Kelvin, and I'm looking for pressure, so ATMs, and then I've got this pounds thing, and I've got argon. So what I need are, out of that pounds, I need to go to moles. So I'm just going to do this in one track now. So 0.34 lb, and then it's 2.2 pounds per kilogram. And for every 1 kilogram, it's 1,000 grams. And then argon is 39.948 grams per mole. So the grams and the kilograms and the pounds, all that stuff cancels out. So now I've got moles. And so I need to get rid of the mole thing. So I'll use my 0.08206 liters, atmospheres, moles, Kelvin. So my moles cancel out. And then I've already got my liters. We just calculated that one as 679.6 liters, so the liters cancels out. And then my Kelvin is 294 Kelvin, so that cancels out. And the only unit I have left is this ATM number. And then this works out to be 0.1 liters. It's only 0.1 because I've just got the 1 sig fig for the 2 and the 4 and the 3. Oh, I'm sorry, ATMs, because it's pressure. ATM. That one's more complicated than I would give you on a test. So, all right. So this next one. So somebody asked me about the cumulative nature of the exam. The cumulative nature of the final exam isn't that I'm going to be giving you questions really from the first couple exams, but on the second exam, I would ask you. I would say barium oxide. Give me the formula. Sulfuric acid. Give me the formula. Now I'm just writing barium oxide and sulfuric acid, and I'm expecting you to be able to write the formula down. That's how it's cumulative. You can't answer this question on an exam if you don't know that barium oxide is BaO and that sulfuric acid is H2SO4. It won't be possible for you to get the correct molar masses. So that's how it's cumulative. So for the formula for this one, it's BaO, and then we're going to sulfuric acid, and then we're going to make barium sulfate, and we're going to make water. So that'll be a liquid, that'll be a solid, that'll be aqueous, and that'll be a solid. Sulfates are soluble except for bariums and calciums. So there's a barium sulfate, so that's insoluble. And anybody who's ever had the pleasure of an upper GI has consumed some barium sulfate. Tastes like chalk. Take 105 and we'll talk about it more. And then barium oxides are insoluble, so that guy's a solid. My sulfuric acid is most likely aqueous, and my water is liquid. All right, so I've got 75 grams of sulfuric acid, and I want to know how much barium sulfate I can make from that. All right, so I've got 75 grams of H2SO4. This question is assuming what? It is balanced because they're all one. We didn't talk about it, but it's assuming what about the reaction? You have 75 grams of hydrochloric or of sulfuric acid, and it's assuming you have enough barium oxide to use all 75 grams. We didn't state it, but in a problem where it's not stated, you just assume that the other one is used completely. The only time you don't make that assumption if they tell you both things or all of the reactants, then one of those is going to run out first and you have to figure out which one. But if they only tell you one of the reactants, then the assumption is there's plenty of the other reactant or reactants to do the problem, to use all 75 grams up. So then the molar mass of this is 98.0795 grams of sulfuric acid and 1 mole H2SO4. And then for every 1 mole H2SO4, we have 1 mole of barium sulfate. Where do the 1 mole and 1 mole come from? Yeah, the balanced chemical equation is just 1 for the coefficients, so we didn't need to do anything with that. And then the molar mass is 233.391 grams of BaSO4. And so I ended up with 180 grams of barium sulfate. Just 2 sig figs on that. Oh, no, it's not. It's 3. So it's 179. My bad. 179 grams. And then the next problem was 80 grams of water. And then water is 18.0153 grams of H2O for every 1 mole of H2O. And then for every 1 mole H2O, it's 1 mole of barium oxide. And then for every 1 mole barium oxide, it's 153.32 grams of barium oxide. And so I end up with 681 grams of barium oxide. So that's how much I would need, how much barium oxide I would need to create 80 grams of water. And again, this one is given plenty of sulfuric acid. Okay.